Okay. Um, so yeah, since you missed a couple of like meetings, let me just give you like a brief overview of what it is we actually talked about.
Hmm.
So, I forget. I think you were there for the man like when we introduced manifolds, right?
Yeah, very, very briefly.
Okay, okay. Um, but yeah, I mean the idea, I mean, the thing is like for physics, if I'm being completely honest, I have not seen anyone like think too deeply about, the definition of a manifold. Um,
Recording in progress.
yeah, like I haven't really seen people care too much about what exactly a manifold is, because at some point you care about, I mean, the objects you care about, and like you move on from there,
Yeah, I'm
right?
kind of like I'm still very confused on how to define a manifold. Like I have a bunch of friends who ask me, "Oh, what is this manifold thing that I keep hearing about?" I'm like,
Mhm.
just think of like a more general square, like if that's possible." And it's
I think to like, I think a better example of a manifold would be a sphere. Um, because I mean, like a square and the plane are basically the same thing. Um,
yeah.
like one is like, I guess one is like bounded, one is not, but whatever. But with a sphere, it actually shows that like even though the local geometry is flat, the global geometry can have curvature. Um, and that's the basis for a lot of interesting just geometry in general. So like for example, um, in Euclidean geometry, there's a postulate called the postulate of parallel lines. Right?
Hmm.
So the idea is parallel lines never meet, right? But this is clearly not true in like spherical geometry, because parallel lines most definitely might meet. For example, if you take out parallel lines, um, like on the equator going towards the poles, right? They're going to meet at the poles, even though they are parallel.
Hmm.
Okay. So even though like local geometry might not be so yeah, the local geometry might not be that interesting. The global geometry is very interesting, and that is what we will care about at some point.
So like that's what like okay, so like what is a manifold? Is like the reason we study manifolds is because of the property of the curvature.
Yeah, I mean, it's just one of many ways to talk about curvature, right? And it's a very nice setting to talk about curvature. Um, it's actually one of the nicest places to talk about curvature. Because I mean, everything is smooth, in some sense. Oh my God, 19. Can I have a 19? There we go. Okay. Um, so I mean, like a manifold, again, I think the definition of a manifold is not really too important, you know. Um, what a manifold is, because if I tell you what a manifold is, it's not going to be enlightening whatsoever. So if you, okay, let me just tell you. So a manifold is a second count. Let me write this down. So, recall, a manifold is a second countable Hausdorff, locally Euclidean. On my iPad stand up, Euclidean topological space. Um, so I mean, like this definition, I don't think is particularly enlightening. Like it doesn't really tell you why manifolds are even things you care about studying, right? Um,
Yeah, it just kind of gave me a bunch of like, oh, it's just a shape.
yeah, and the idea is that like we've studied like okay, when I say we've studied, I mean like historically. We've studied like surfaces in two dimensions because we really care, sorry, in three dimensions because we really care about that stuff. For example, if we want to make a map of the world, we need to know, can we even make a map in the first place? Like, is this a possibility? Um, and then we can ask, okay, can we make a map with the property that it doesn't distort like distances? Because if it distorts distances and angles, then it's very inconvenient for navigation, right? Um,
Mhm.
so that's why we've studied like these surfaces. And now the idea is, okay, we've gotten a pretty good grasp on these surfaces. Is there a generalization of what these objects are that might tell us more about like other fields of study? Right? At least that's the way I like to look at why we study manifolds or why we even care about manifolds. It's not like for me particularly, um, I think even in physics, for a lot of physics, like physics doesn't really care much about like what a manifold is specifically. It's like the what can you do on a manifold that is important. Um,
Yeah, yeah, I think that's like I feel like you know what like manifold because I've been studying this stuff for a while. Like I've been studying like manifolds for a while, like what they do rather than what it is.
mhm.
This definition personally has never made any sense to me. Um, like I couldn't even tell you what a Hausdorff is.
I mean,
Uh,
Hausdorff just means that like any two points can be separated by open sets. So you can find disjoint
oh.
open sets that like separate points.
Oh, okay. So it's just like, you know, the typical topology thing on an open set, we have so and so shapes that can blah 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 into each other. Yeah, okay. So that makes sense. But like thinking of like the idea that a manifold is like structure preserving or stuff like that, and then thinking about the linear algebra between thinking about the linear algebra of manifolds and manifold geometry has actually really helped me like in my actual physics classes and like trying to describe higher level physics to like say my friends for example who are all studying like econ and stuff like that
Yeah.
who are interested in this sort of stuff but you know they don't really doesn't really make any sense. So what I would ask is like you know like what can we do like with this definition of manifold to make it more accessible I guess because this like it still doesn't really make any sense to me like
Yeah, no,
it is.
that's fair. So, um, I think the best way to like talk about manifolds in general is like, depending on the context, right, is examples. Because I think like certain examples of what manifolds are is a lot more enlightening than this definition.
Mhm.
Um, so for example, every sphere is a manifold, right?
Yeah,
So even though it's locally Euclidean, by local Euclideanness, I mean like if you zoom in to a point, like really close to a point, it looks flat, right? Or it looks like Euclidean space, right? So anything that looks like that looks locally like a Euclidean space, I would say is a manifold. And then like this second countable and Hausdorff properties are nice, but they're a lot of times you don't actually even care about second countability. You actually care about something called
sorry,
para.
what is second countability? Like second countability describes like I know what first countability is. It just describes what's it called? Like it just describes, I guess, like I guess I really don't know what first countability is either. Like I
Yeah,
just know
so
countability.
second countability just means that I can take like I have a basis for my topology that's
Mhm.
countable. So it's like,
Really?
yeah, that's all that means. But the thing is, we don't actually care about that property specifically. We care about another property called paracompactness.
Hmm.
And if I'm being completely honest, I don't know what paracompactness is. Um, like it's to that extent that I think a lot of these things are irrelevant. Like at least the main definition of a manifold, like a lot of the properties is like once you've seen them, you like store them in your head and you never really think about it beyond that. Um, it's like but paracompactness will find its use when we talk about integration. Which I was thinking that I might do today or on Saturday. We'll see.
Oh, okay. So it's like it's a space. Okay, so if you think about like a topological space with any open cover, so say like take the globe for example,
Mhm.
it has an open cover.
Mhm.
Um, then like paracompactness just says that every refinement of that open space is locally finite, which would make sense in terms of integration on manifolds.
Yeah, so the reason you actually use that property over second countability is because you can define something called a partition of unity. Um, and basically the idea of a partition of unity is like, say you have some like um open cover, right? Um, you now for each open cover you define a function, okay? And the idea is that you're breaking up the identity function, okay, into a bunch of different functions. Okay.
Mhm.
Um, and the idea is that paracompactness allows you to take like a finite number. Sorry, because you have to add up all the values of these functions, it would be very inconvenient to talk about like infinite sums because then you'll have to talk about convergence and so on. So if you look for paracompact spaces, your partitions of unity are locally finite, right? So at each point, you only have a finite number of functions that are non-zero. So your
Mm.
sums become like, finite sums, and they're a lot nicer. Um, but yeah, so I think like manifolds, like if you want to think of manifolds, just think of like blobs in space that are not too bad. And if I zoom in, they look like a flat space.
Oh
But
yeah, like the universe. So I just think about like the transformed universe that's locally nice, but like on a global scale, very interesting.
yeah, like again, with just manifold theory, a lot of local properties are not as interesting to me. There might be some interesting properties, but I haven't really looked into it that much. What I care more about is like when I like give these manifolds more structure and I do calculus on these manifolds, like what is happening, like um, so yeah. Um, And that's why I wanted to talk about like Riemannian geometry, because Riemannian geometry will talk about things like curvature in a more like it'll actually talk about curvature. You can define a like practical notion of curvature on a Riemannian manifold. You can talk about lengths, you can talk about angles, you can talk about a bunch of stuff. Um,
Okay, so let's do that.
yeah, but the thing is, there are a couple. We'll talk about Riemannian manifolds, I think, next week. There are just a couple more things that I wanted to get through, and again, these are just like um, prerequisites that I mean, it's not really prerequisites at this point. These are like genuinely new concepts. Um, yeah, these are genuinely new concepts. Okay, so last time, um, we defined like we took the tangent bundle, like TM, right? If you remember what the tangent bundle is, it's like the fibers. It's a vector bundle with fibers being the tangent spaces. Um, and then you give it like a certain twist in a way that on the intersections, tangent vectors transform with the Jacobian of the change of basis or the change of variable. And then we dualized it, right? We dualized it to get the cotangent bundle, T star. Okay. Um, we will see that, yeah, okay, so before we get to why we talked about the cotangent bundle, the fibers of the cotangent bundle were the fibers of this space, but they're duals. And then we patched them together in such a way that when you do a change of variable, they transform by the inverse Jacobian.
Mm.
That that's basically what dualizing means. It's like instead of transforming by the forward, you transform by the backwards. Um, okay, so now one might ask, okay, why even care about the cotangent bundle, right? This is a very valid question to ask. Like, why do you care about the cotangent bundle? Because I mean, the tangent bundle has a more physical meaning, right? Um, if I look at sections of the tangent bundle, I get vector fields on my manifold, right? In some sense, the tangent bundle seems like a more natural object initially, right? Because we can talk about things like vector fields and so on. But we'll see that like the cotangent bundle is as important as the tangent bundle, if not more. Okay. Because it will allow us to do things like integration. If you remember, the determinant function, which talks about, the area, like how areas transform when you do linear transformations,
Hmm.
um, that thing wasn't a vector necessarily. Like, I mean, it is a vector in some vector space, but it is much more useful to think of it as a multilinear map on that vector space. In other words, a tensor, right? And in our language, it would be a n0 anti-symmetric tensor, right? And the cotangent bundle is just the first step to that point, like to get there, because we need to take like the wedge products of these the same way we did when we talked about linear algebra. Um, and that's sort of the goal for today. We will take, I mean, I'll brush over the details because yeah, because I mean it's the same thing as the cotangent bundle, and we talked about the cotangent bundle in pretty good detail last meeting. So if anything, um, yeah, you can just look up that thing on the website because I did post the meeting notes on the website. Um, okay. Um, yeah, before starting, are there any questions?
No, so far so good. Just I guess a quick question, I guess is like so I guess we're just trying to build a more general determinant function.
Basically, yeah,
Yeah.
basic. Um, because we saw like in when we talk about like integration normally, like on flat spaces, um, the determinant function plays a vital role, right? When you're talking about the change of variable formula.
Yeah, because it
Um,
is like the first differential, the Jacobian, second differential, the Hessian, and
yeah.
et cetera, et cetera.
So
Yeah.
so the you want to somehow you want to when you're building a theory of integration, you like change of variable is one of the most useful formulas there are. So an integration theory without change of variables is not that nice to work with. Um, okay.
Well, yeah, I
Um,
could imagine like we have no way of transforming our not so nice shape into a nicer shape to give
yeah,
it
and then
properties, right? We would leave a lot impossible.
yeah, exactly. And that's just I don't know that if an integration theory that way might be interesting in the sense that okay, like what results can you derive out of this? But in any meaningful application for me or in for physics, I don't think necessarily it would be the right decision. Um, okay. We also talked about sections. So sections, right? So what is a section? So if you have some vector bundle, right? If you remember, if you have a vector bundle like this, um, then a section sigma of this bundle. Actually, I guess this doesn't actually have to be a vector bundle. All it has to be is that this map should be surjective. Oh, sur surjective. So if it's surjective, this definition hold. Like this
But a
definition would make.
surjective map of what? Like, I mean, it does kind of help that it is like a vector bundle. Like, are the vectors multidimensional?
I mean, that's the thing, right? Like with this definition doesn't actually matter. This thing could be literally any set. This thing could be literally another like any other set. And then a section would still make sense because all a section is
Yeah.
of this surjection is a so yeah, section of this surjection is a right inverse. And what I mean by right inverse, I just mean that pi composed with sigma is the identity function on M. That's it. So basically, at each point on M, you give a vector or some object in the fiber of that point. Um,
Okay, and so I guess in this case, E is like the fiber and M is the vector.
no, the fiber would be so EP, so pi inverse of the set P would be the fiber,
Okay.
and like V in EP is a vector.
Oh, yeah, yeah, yeah.
Yeah.
Okay.
So sections of TM are vector fields, right? Because at each point you're giving a vector.
Yeah, yeah,
Um,
yeah. So I guess like the whole space is a okay.
Sections of T star M are called covector fields. Um, Sections of M composed N are maps from M into N. Okay. Um, and now, if you give E and M like topologies, you can talk about like the continuity of this section, right, in the usual sense. Moreover, if you give them smooth atlases, if you make them into like, manifolds, smooth manifolds, you can talk about whether this section is smooth. And this is like these are the sections that we'll care about most often. So um, we denote by this to be the space of X. How do I want to write this? Like X section of Tm into M and smooth. Okay. So at any point, basically, a section would give me a vector in such a way that it's like smooth. Right? Um, I'll call omega 1 of M to be the set of omega, which are sections of T star M into M and smooth. And then an exercise is to show that um, sections of M cross R uh, is the same as the space C infinity M. If you remember, C infinity M is just the space of smooth functions from M into R. Um,
Oh, okay. Like I guess the reason that makes sense is because we're taking all I guess all sections of the tangent space and the cotangent like of Tm and T star M. And since all of those sections by definition of the set have to be smooth.
no, not all sections are smooth. Most
Well, I mean,
definitely
this is
not all.
X section of Tm to M and smooth.
Yeah, so not every vector field is a smooth vector field, right?
Yeah.
Like you could have discontinuous vector fields. You could have vector fields that just do random stuff at each point.
Hmm.
So we specifically care about the space of the smooth vector fields. Because we'll see that it allows us to talk about like the motion of particles, for example. Um,
Yeah, because it like motion of particles is not a discontinuous random jump.
I mean, like physically they are like physically. Like for example, if I push a particle all of a sudden at one point, like the velocity of that particle does jump up discontinuously, right?
Yeah, but the displacement isn't.
No, so I mean, yeah, the displacement doesn't, but the field, the vector field, is your velocity field, which
Hmm.
does jump discontinuously. So not all like sections need to be smooth. Um, but the setting we will work in is like an idealized version of reality where objects have been moving forever.
So what
Field,
is a covector field? Like what is a covector field?
I mean, a covector field is just at each point I give a cotangent vector. So I have like tangent vectors, and if
Hmm.
you remember, you can take the dual of these tangent vectors to get
Yeah, and you get the
covector,
cotangent. Yeah.
right? So instead of giving you a tangent vector, I just give you a cotangent vector.
Hmm.
There are some visualizations of the cotangent vector with like planes and how many lines cut through those planes. I am not really a fan of those because I don't really understand what's going on. But if you wanted to look into it, there's a book by John um, Bays, I want to say. That's how you spell his name. Called Gauge Fields, Knots, and Gravity. That does talk about it, like at the beginning. Because I have the book on my shelf. Let me show you. Like, oh, yeah. So I did get his name right. Um, this book is very good, but I would be a little wary with it sometimes because it does have a lot of typos. Um, so yeah, you just have to be careful. So oh man, okay. How do I? Okay. Um, So as you can see, you have some tangent vector, and then the cotangent vector is like this plane of lines, and the value of the cotangent vector at the tangent vector is how many lines it goes through. Um,
Oh, what? Really? Wow.
yeah, so I mean, he does describe it for like, like when he describes it from here into here into here, and
Okay.
there are a couple of exercises as well. um, that you could do to convince yourself of this. Um,
So for the exercise, then, if M, like, okay, so would it just be like M? We define M as like the set of all vectors containing tangent and cotangent vectors, and since we map these tangent vectors across a continuous function, like a continuous vector field or something, then the amount of cotangent vectors is
no, so
the
it's
amount
like,
of tangent vectors going through cotangent vectors are the exact same. And so the surface is smooth, therefore M by R, or the transformation T defined M by R, defined by M by R, or the matrix defined by M by R is comprised or, contains as many components as well, the set of all continuous functions.
I mean, with this, it's like if you write out this definition of section, right,
Hmm.
you will see instantly why this is the case. Because sections will quite literally um, be functions, like functions in the sense that we're usually dealing with them as. Um, so this, if you write it out, like you'll see, like it is very easy to see what it is. Um, but yeah,
Isn't or is very easy.
it is very easy. Um, I think okay. With covector fields, like okay, like vector fields are easy to visualize, right? Like because you've like worked with vector fields a lot. Even if you didn't know you're working with vector fields, like you have worked with vector fields before, like in an E&M class, for example, right?
Hmm.
Um, so you have a lot of intuition about what a vector field is. Covector fields, on the other hand, are like a lot more, I don't know, they're a lot more mysterious, in my opinion. Um, and I, what I think I'll do is we'll do a lot of computations with these, um, just to sort of, get the idea of what it is. So I think once I talk about a bit, like I just want to like introduce the other tangent bundles. like the other tensor bundles. And once we introduce those, I think let's do some computations. Like let's do some like rigorous computation. Okay. I mean, let's do like some explicit computations. Is that fair?
Yeah, 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 okay.
Okay. So then like I hopefully then you'll at least know like if you have like a tangible way of working with them, maybe you can develop some intuition. Because
Mhm.
as of right now, I don't really have a good intuition. Like no, I mean I have good intuition of what it is just because I've been working with them for like 3 years now. 3 to 4 years. But I don't really know like my intuition is not that good where I can give you like anecdotes of what this actually is, like a way to visualize these things. Um, because as a mathematician, at some point I decided that it is not worth, for me at least, um, visualizing what covector fields actually look like. Because that, like, no visualization has really helped me. Um, so. Yeah, we will do some computations like at the end uh for of today. Okay. It's okay. I mean, sections of bundles, um smooth sections of an R like of a vector bundle will be denoted like this. Unless you're talking about, the vector fields or the covector fields. Um, these objects also are called like sections of like covector fields are also called differential forms. Okay, so this is also the space of one forms. And here we hide the word differential because we assume that our one forms are smooth. Okay. Um, do I have anything else I want to talk about here?
So smooth, really like the intuitive way is just like continuous, but on a more dimensional scale, I'll say.
I mean, smoothness is like differentiabilities, right? So.
Yeah, exactly. Yeah, it's
So for example, like you could have some function that looks like this, like this is continuous but not really smooth
smooth.
because of
Yeah.
points like this, right? Uh,
Mhm.
so smooth just means it quite literally is just like smooth. That's one way to look at it. Um, but okay, I don't think I have any other thing to talk about um, in terms of like these vector bundles just yet. So let's generalize this quickly. We won't really care about most of these generalizations. They are just there because there's like this one idea that I like would like to introduce, and that's the main reason why a lot of these exist. Because like once we start doing physics, we are not really gonna care too much about okay, is this a 1-3 tensor or a 4-1 tensor or a 1-4 tensor or whatever. Like we won't really be um too strict on like what the actual order of these tensors are. All we care about is that these are tensors and why they transform the way they do, at least just to get an idea of like what it is we're doing. Okay, so following a similar logic to last time, um, what we're gonna do is we're gonna take the tangent bundle. So I'm just gonna take the tangent bundle. I'm just gonna say it. Take TM, right? Um, and then the thing is we used some representation. Um, we used some representation of GLRN, right? Uh, to get cocycles, um, G alpha beta, um, for like the gluing of M. Um, I don't think you were there for when we discussed this, right?
I saw this one online, so
Okay.
yeah,
Um,
I read about I watched the lecture for it online, so
okay. Okay. So what we're gonna do now is we took the standard representation of GLNR, which was just mapping every vector to like every map to itself.
Hmm.
To get T star M, we just dualized it. So we took that representation. Now, to construct the tensor bundles, all we're going to do is we're going to take some tensor representation of this. Okay, very simple.
Oh, this is really not even that difficult.
I mean, yeah, like from a point of view of like, okay, we take a map and then we just take tensor products. From that perspective, it's not really that complicated to like see what's happening. But when you like, that's why like with a lot of these things, it's like when you do the nitty-gritty details is when things actually get more complicated. And that's what leads to like interesting topology
Yeah,
in the
yeah,
first.
yeah, yeah. Like seeing, okay, like at a high level, or I not really high level in terms of complication. I mean high level in terms of like the bigger picture.
Yeah.
Having this is like, okay, so taking TM is like you just take the standard representation, then you dualize it, then you get, and then now the tensor space is just, oh, now you just need a tensor representation. Yeah, I can see
Yeah.
how like on the small scale of like a proof or something where you need to like prove these things, then you get really interesting details because, well, I guess the proofs are very detail oriented,
Yeah.
or as most proofs are, definition oriented, and the definitions leave a lot.
Yeah, I mean like once you've like done your due diligence to like make sure you understand whatever it is you need to understand, um, a lot of the times you tend to just forget about a lot of the smaller details, right? Um, but you keep like the bigger results in mind. I think that's a nice, I don't know, that's just how I do math. I tend to just keep like the bigger pictures in mind and then try to fill in the details on my own. Um,
Yeah.
Also, regarding interesting topology um, of the tangent bundle on the in the exercises that I posted yesterday, um, I've outlined a proof that the tangent bundle of the sphere is non-trivial eh, in the sense that it's not just this thing.
Well, that would make sense because at every point I guess you have infinite amount of tangent vectors.
Yeah, but this space also has an infinite amount of tangent vectors. And as sets, this set and this set are actually the same. As sets they are, but not as smooth manifolds. Um, and it also shows that the sphere is not a Lie group. Um, but
Hmm.
you can go check out that you can check out the
Yeah,
exercise,
I guess I'll have
do
to
the
because that sounds like
exercise,
a
and
problem.
um, yeah. Okay, so now all we're gonna do is we're gonna take so we can now we take tensor representations, right? Um, so we get a map rho. Um, what we're gonna do is we're gonna take the standard tensor representation, um,
Hmm.
which is given like this. So it takes A, and all it does is it maps it to the k copies of the dual. So remember, you have to take the dual, and then you also have to invert it. If you forget to invert, this thing won't be a representation. And then you tensor it with L copies of just the vector itself. Yep. I mean, you can now, this is an exercise for you, show that this is a smooth representation. Uh, it is the hard part is showing that it's a representation. Once you do that, it's smoothness. I'll let you think about why smoothness follows instantly. Um,
Hmm.
so then we define tensor bundles, um, TKLM. Okay. Some people like to call this TKLM like that. Um, I tend to get confused with this, so I will stick with this. But note that these are the same, same thing.
Hmm.
Um, Okay, so I mean, like, again, I'm not gonna an exercise for you, I guess, would be to, find the explicit cocycles of this, if you would like. I mean, the cocycles are basically here. Um, and I mean, I just play around with it, like get your hands dirty with it, um, and stuff like that. So I mean, I'll let you like actually think about what this space is. It again, in most cases, we don't really care too much, if I'm being honest. Um, but okay, let's
Is the
now
map
look at,
G or
huh?
the map rho we've defined, is that bijective?
Um, is it bijective? I doubt it because this says that every tensor is decomposable, which is not true.
Mm.
Also, it
So
can't be
we're taking
bijective. It can't
a
be
tensor
surjective.
in A and we're decomposing it.
I mean, it can't be surjective because this as a vector, this as a um, this thing has dimension like Rn squared. This thing has dimension like um, Rn to the power k to the power L squared. So as vector spaces, these two things would they just can't be surjective.
Yeah, okay, so then your second statement as to like, oh, then we're saying that all vector, then we're saying that all tensors are decomposable, which is like this is very obviously not true.
Mhm.
Is that like why smoothness like immediately follows because we've defined the second portion as decomposable, which means
Yeah, basically, because then you just take projections and then like it's smooth on each component. And since it's smooth on
yeah.
each component, it must be smooth. So yeah, like that's the idea there. Um, but okay, I mean, again, in physics now we care about, and even in math, a lot of the times, a lot of at least for me, when I like learn something like this, I want to see like, okay, locally, right? In terms of things that I already know, right?
Mhm.
What does this object look like? Okay. So so let's talk about that. So in local coordinates, so by local coordinates, I mean, you have some u phi, some chart with coordinate vector fields, um, partial like psi, and coordinate one forms dxi. Um, since you weren't there last time, I'll just, tell you what these are. Like, so at each point, right? Because remember, this is a section of a vector bundle, so I need to describe it at a point.
Mhm.
And now at a point, this thing takes in the tangent space of U, which is the same thing as the tangent space at M, and maps you into the tangent space um, at phi of U, sorry, phi P in R. Sorry, no, I'm overcooking here. Sorry, this should just be into R. Okay.
Mhm.
So that d dxi, I'll leave the point P because yeah. On the coordinate vector field partial partial j is just delta ij.
Oh, why is it the delta function?
Because I mean it's just the like this isn't like the delta function in like not like it's not the distribution delta function. This is one if I and j are the same and zero if they're not.
Yeah,
And
yeah, 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 yeah. Not like no, I mean it's like what like the Kronecker delta function thing.
yeah, oh yeah, I mean that's just the definition of the dual. Like you have some basis and then you take its dual basis. Its dual basis is precisely the basis that satisfies this property.
I gotta be honest with you, I find linear algebra and I guess differential algebra and geometry like fantastically interesting.
I mean, I find it interesting enough to like do a whole reading group that's on physics. But in reality, I'm just talking about math. So you're not
I
alone.
mean, technically, I mean, if you teach it this way, then we can do whatever physics wants because physics just kind of assumes a bunch of these things.
I mean, yeah, like I am motivated by physics. So like I'm not a mathematician in the sense of a mathematician. I'm a mathematician who is driven by physics. Right?
Yeah.
Like I care about the physics as well, right? Like and that's what like got me into geometry in the first place. Um,
But you know what? I guess because like being an undergrad, right? We don't actually do like much real physics in undergrad. Like we have to wait for grad school to do like the real stuff. So I guess like over the course of my undergrad career, I really want to take in as much theoretical math as possible.
yeah.
So when I get to like the real physics, like I can go tell the prof like, oh yeah, I learned this in like first year.
I mean, like I I don't know. I wouldn't fall into a trap of, calling things real physics or real math because mm, no.
Technically, it's all real. I just mean like the most up-to-date current modern physics that we don't get to really talk about in
Yeah.
undergrad physics because we're really busy learning like the building blocks that lead up to it.
Yeah, I mean that's fair. That's fair. Um but yeah, okay. So in local coordinates, if you take omega, right,
Mhm.
to be um so I know I said this confuses me, but I have this in my notes, so I'm gonna uh stick with it. You take the thing at a point, right? And now you want to be like, okay, what does this tensor actually look like? Okay. Like, because I
That's a
know
great question.
this is a KL tensor. I know that. Wonderful. But what does it actually look like in these local coordinates? Right? And it turns out that it's just you have a bunch of functions called I mean from omega 1 up to k, j1 up to L at this point P,
Hmm.
um, dx I1 at the point P, tensor with dx I2 at the point P, you know, dx I k at the point P, and then you tensor in um the vector, like the vector part at the point P, um partial J, so this should be J1.
Mm.
It'll be
Why are
JL.
you taking, why are you doing it twice?
I mean, because I have like L tangent
NK.
vectors and K cotangent vectors. Um, so I mean, okay, this is sort of in local coordinates what my object looks like. Um, and now it might be like, okay, this is not any better um than before. You would probably be right. Um, but I don't know, what am I trying to say? Now you can think of like tensors the way you did in linear algebra. There's no difference, right? You have components of a tensor, and you can like discard, like you can forget about all of this because now you're working in some basis, right? Um, and and yeah.
Yeah, I was gonna say this looks like a basis. This
Yeah,
just
I mean, and yeah. So this is a basis of the space of this space, at this
yeah.
point. An exercise. This is no,
If you
it,
say show this as a basis, I will throw a book at you.
I mean, showing that this is a basis is, I would say, by definition, because that's just how I look at tensors. So I guess it depends on what your definition of a tensor
I
is.
guess my prof would say prove the definition.
Yeah. My exercise actually is, suppose you have suppose um V psi is another coordinate system. How do the components transform. How do these objects transform when you do a change of coordinates? Um, and if you're struggling, like if you try this question and you're struggling a little bit, I would suggest you go back and look at um, when we did this for linear algebra.
No, okay, so here's like what I'm thinking. Like even if I were stuck on this, what I would think of is like how we generally treat change of coordinate like in like naturally, like I guess in calculus
Yeah,
with
yeah, and that's sort of the idea. Like you, oh shit, you know how these things transform because they transform with like chain rule.
yeah.
So do these. So you just it's just like putting two and two together basically to get how these things transform. Um,
Mhm.
but it is a very good exercise to do it once and only once. Because I don't know, it's not really enlightening after a point. Um, but okay, I mean, th this is all wonderful, but again, not really the nicest way, to treat these things. Um, also, let's just give another characterization of these. Now, omega is a like a covector field. Sorry, is a KL covector field if and only if for all points in M, um, and charts U phi around P, the component functions are smooth. Yep. This now allows us to look at so we can now like this sort of way of looking at this um allows us to we can like allows us to look at these things um as C infinity M linear functions. Linear function um as a C infinity M linear function. Omega. Okay, now let's see, right? So this object has to take in a vector field. This object also takes in a vector field. This object also takes in a vector field. This object takes in a one form, and so on. And like this object takes in a one form. So the idea now is that you can think of this as a map from like k copies of vector fields, right? And L copies of one forms. Okay, so here you have k, here you have L, and this maps you into C infinity M. Okay. And the idea is like it's not only linear over the real numbers, it's like linear over the module of C infinity functions.
So doesn't that actually just kind of solve the entire exercise to begin with?
Um, like this one?
Yeah, doesn't that just kind of tell me what I want to know anyway? How it's like how they're transformed? Because
Not quite, right? Because I mean, like this just tells you that okay, this is a linear map or like a C infinity linear map.
now
Like,
wait, now I'll explain my reasoning why.
yeah.
Because if we have a linear mapping from all of these copies of vector fields in one forms, we're basically talking about how this object is transforming.
Not quite. It's like okay, when you look at linear algebra, right? You can look at a matrix or you
Hmm.
can look at the linear map in finite dimensions, right? Like these two concepts are basically the same. The map doesn't really tell you if I do a change of like if I do a linear change of coordinates, how does my matrix transform? Like the map doesn't necessarily tell you that, right? Similarly, in this case, I mean, okay, I guess it does, but like again, you have to like work it out,
Yeah,
right?
you define the okay, because I don't have any like terminology with tensors yet, but you define the matrix as follows, and then you show that the matrix under these conditions produces I guess, of like, produces something, produces a function that is included in C infinity M, which actually just spans C infinity M. And so by our like my current understanding of topology, I can at least transform the thing into any nice shape that I want it to be.
Yeah, but the thing is, this is saying this is true for any coordinate system, not only the nice ones.
Yeah, I know. It takes it from an like whatever BS coordinate system and
Mhm.
moves it to a nice coordinate system.
I mean, what I was actually like thinking about when I asked this question was if we go here
Oh,
um,
okay.
and we look here. So we have like dxi and d tilde I, right?
Mhm.
Um, and these are the corresponding dual, like dual vectors. And then you have this like prefactor out front. So this object transforms by, you know, the inverse. So this is like the inverse uh, change of variable, right? Because our you're taking the derivatives of the x coordinates of our coordinates with respect to the transformed coordinates, which is like the opposite of what you would think of. So what this tells me is that the coordinates themselves of like cofield, like covector fields, transform by the inverse of this. But the inverse of the inverse is just my Jacobian. So the components of my differential forms change by like products of Jacobians rather than products of.
Yeah, so you wanted me to like prove what we were basically talking about at the beginning was the inverse Jacobian.
Yeah, so I just wanted you to like, go through it, like actually tell me like the rule, like the change of a variable rule.
Oh, okay. So not like okay, what it does is like, oh, you actually go like, oh, this is like the inverse Jacobian of blah 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 blah
You
blah.
know what? I think what I'll do is I will put this as an exercise for the next homework.
There's a lot of really fun exercises that I've been going over with these problems, and I'm very excited.
You should send me some. Let me
No, they're in
oh,
your
okay, I see.
like they're in your thing, yeah.
I see. Thank you.
Yeah, I
I
don't
like
have enough knowledge to pick exercises because you should know this.
I mean that the way you like learn how to do that is just, um also I'm looking at like problem sheet one. And actually, never mind. I don't actually tell you how to do it. Okay. I'll outline it. It's again, it's like it's just an annoying computation. It's not deeper than that, I think. Um, it does have a lot of physical meaning though. Um, especially in GR. And it's one of like the most important things that, we can really talk about. Um, but okay, let's now actually introduce. I didn't expect to get to Riemannian geometry, but I don't think I'll do Riemannian. I'll just introduce what a Riemannian metric is.
Do you want to introduce it and then because I have to leave at 5:30.
Okay.
So
Yeah, so I'll just talk about this one thing. Like now the next thing in my notes anyways is like examples of tensor fields and like why we even care, you know. Okay, let's go over examples quickly.
mhm.
Okay. So the most important one that we're going to talk about is a Riemannian metric. Okay. And what is a Riemannian metric? A Riemannian metric, so it's G. Okay. And it is a smooth section of this tangent of this bundle. Okay. Um, that is um, symmetric, positive definite, and um, non-degenerate. So, I mean, if you look at it really carefully, this is just the definition of an inner product.
Mhm.
Symmetric, positive, definite, non-degenerate, right? And that's basically what it is. The idea is that GP is a map from TPM cross TPM into R, that is an inner product.
Hmm.
Okay. So the idea is at each point we have like a tangent space. Our metric is not a metric in like the analysis sense, but it's a metric in the sense that it gives me like an inner product structure on my tangent bundle. Okay. And it's like symmetric because inner products are symmetric. It's positive definite because inner products are positive definite. And it's non-degenerate because again, inner products are non-degenerate. Um, so locally, G is equal to Gij dxi tensor dxj, right? Some people put a 1/2 here. I'm not going to be too picky about that. Um,
Is there a
where,
reason for one
yeah,
half?
the reason is like symmetry. Um, so it's like if I swap the indices, I'm like double counting basically. Um, but I mean, for our applications, it won't actually matter too much. Um, So yeah, I mean, this is what a Riemannian metric is from the point of view of like tensors and like a tensor field. So it turns out like okay, one of the most important examples like to define the notion of lengths on manifolds, right? We are using a tensor field, and we'll see how this will define like a notion of length soon.
Is that how we like define like length the most general way?
I mean, I would say the most general way to define a length is in like a metric space, like the analysis metrics, because those will cover this. Like this is an example of that type of metric.
Oh, okay.
It's
But
just,
I mean, like physically, I mean physically, not like theoretically. I mean like physical application of this.
I mean, there are a lot of metrics that are used in physical applications that don't come from inner products. Um, if I'm not mistaken, I think there's a metric called the Manhattan metric or the taxi cab metric. That does not come from an inner product. Let me just make sure.
Yeah, we need to like at least in physics, I feel like hire a naming committee because I don't really understand where these names come from.
I mean, the taxi cab metric is actually a very good name. Because the idea is that if you have 2 points here, the distance is just this plus this.
Uh-huh.
So it's like you're a taxi in Manhattan where there are only like, it's like a grid. Like Manhattan is
Yeah, the
a grid.
grid roads. Okay.
So it's like, what distance are you traveling on the road? So, but this doesn't come from an inner product. And I think you can check that it doesn't come from an inner product because um, it doesn't satisfy something called the parallelogram identity, which you will learn in 247. So
Yep.
I will not spoil that for you. Um,
Shame.
okay.
Shame.
So yeah, that's what a Riemannian metric is. We'll talk a lot about Riemannian metrics. We'll talk about curvature associated to Riemannian metrics. We'll talk about um, you know, geodesics on Riemannian manifolds. Um, we'll see how the local structure of Riemannian metrics is actually very interesting. So you can't apply a Gram-Schmidt-like procedure on a Riemannian manifold, and we will see that. Um, and that's because of curvature. Like curvature obstructs one from doing this. Um,
Graham Schmidt is to orthogonalize things.
yeah, yeah. So the idea is like you want to get rid of these like functions so that it just looks like dxi tensor dxi. Uh, well, I guess dxj delta ij, But
Oh,
it turns
sweet.
out that you can't do that globally. Like you can do it locally. The proof follows from. Actually, can you do it locally? I'll have to look into it. I'm not actually sure. Um, and then the second important structure that we'll talk about is called a symplectic form. Um, so a symplectic form, um, is omega in, for now, this will be also in this space. Um, that is almost the opposite of this. So it's like the anti-symmetric, non-degenerate. Let me see, what else do you need? So it's, why am I forgetting symplectic forms? Like symplectic geometry is what I study. Uh,
That's okay. Just come back to it next time because I got 5 minutes.
oh yeah, okay, it is. It's just a non-degenerate two form. Okay. Oh yeah, I guess the thing that actually makes it a symplectic form, um, is closed. Um, I somehow forgot to put that in my definition in my notes, so I will go and change that. But we will talk about what closed means later because I haven't introduced like I haven't introduced the right things to, talk about
Is it
C.
like a closed interval, open interval, that sort of thing?
No, 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 it doesn't have anything to do with that.
Hmm.
But omega can be written as omega ij dxi wedge dxj, if you remember the wedge product from, um, you know,
That was a
linear
while ago.
algebra.
But yeah.
This is just wedge from,
Do we also do that in 247?
wedge products? No,
Mhm.
no. I don't know why. Um, you talk about anti-symmetrization, which is actually just the wedge product, but you don't call it the wedge product. Uh,
Okay.
so,
Sure.
um, if you're interested in what closed means, it just means d omega equals 0. You can search up what that means, um, to prepare for, the next couple of, meetings. Um, but yeah, so I my main goal for today was to, give you these examples of tensor fields to really show you that what we're doing, like the point of generalizing, sorry, generalizing actually has a point. It's not just, unnecessary because it might seem that way. But it isn't. Um, but yeah, next, so on, you're not gonna be there on Saturday, right?
Saturday? No, actually, this Saturday I will be there. Friday I can't make it
Okay.
because we have like a recruitment event that we have to go to. But
Okay.
Saturday, yeah, definitely I'll be there.
Okay, yeah. So on Saturday we'll actually talk about like, we'll talk about differential K forms.
Hmm.
Um, and I might talk about, um, no, actually I shouldn't. Um, I'll talk more about like vector fields. We'll talk about like, commuting vector fields. Um, we'll talk about something called we'll talk about taking derivatives in the direction of vector fields and stuff like that. Um, so yeah,
Sorry, what? How do you what? You take
I
a
mean,
vector? Oh, okay. Sorry, sorry. I'm thinking of like vector spaces. Like, there's no way you can take the directional derivative of a vector space.
yeah, no.
Like,
So the idea is we'll take a vector field, we'll take functions, we'll look at what it means to take the derivative along a certain vector field, and we'll introduce one of my favorite formulas, called like Cartan's magic formula. Um, but yeah,
oh, I've heard many horror stories of said formula, but
I mean,
sounds fun. Count me
it
in.
it is a very good formula. I don't know if I'll prove it. I'll send you a proof that I came up with for it. It's a very
Leave it
standard
as an
one.
exercise and then put it in like the chat.
I might do that. I'll see like what we should do. Um, but yeah,
Because if I know how to prove it, then I can just pull it out on any random linear algebra exam and I'll be very happy.
I don't. So the proof honestly is not that enlightening. Uh, it uses
Hey,
the
it's
it,
prove it's proven. If it's proven, I can use it.
yeah, but again, the proof is very long. Like you have to check um four things that each take, a little time. Um, but we'll
That's
see. But we'll see. Like um, it'll be like the unique function that satisfies property one, two, three, four, and then you check that any other like you check that Cartan's magic formula also satisfies one, two, three, four, and then they have to be the exact same thing because they satisfy the same properties.
Mhm.
Um, so yeah. Okay. So that's there for now. On Saturday, like I said, we'll mainly talk about vector fields. We'll keep differential forms out of it for a bit. Um, and yeah, I mean, do you have any final questions?
No, I'm good. I'm good. Thank
Okay.
you, Kush.
Yeah, just let me know on Discord.
Okay.
And I'll see you on Saturday, man.